Alright, in this video we're going to take a look at finding the probabilities of independent events. In the last video we looked at calculating probabilities using the multiplication rule. So in this one we're going to focus on what are known as independent events. So two events are independent if the outcome of the second is not affected at all by the first actually happening. In other words, the second event's chances of happening are not impacted at all by the first event actually happening. So for two events A and B, we have our multiplication rule says the probability of A and B is the probability of A times the probability of B, and that is for independent events where the chances of event B happening aren't impacted at all by A happening. So some examples of this would be rolling a fair die and flipping a coin. So the outcome of flipping a coin doesn't impact at all what the outcome of rolling a fair die is. Another probably more useful application of this as far as any students are concerned is if you have a multiple choice test with, let's say, A, B, C, and D as the answer choices, and if the answer choices that the teacher, professor, or whatever they're using to generate the test truly does generate the test randomly and generate the answers randomly, then you might have like 3 or 4 like of the same answer in a row. If it's done truly randomly and they are independent of each other, then there's no reason to believe that the next one is going to be a particular outcome. For instance, if you flip a coin 5 times and 5 times it lands on tails, there's no reason to believe that the next one is also going to be tails, assuming it is a fair coin. So if you have like 3 answers in a row that are, let's say, C, it doesn't necessarily mean the next answer is going to be C. Nor does it mean that you should pick C if it's truly done randomly. So everyone has an equal chance of being selected for a multiple choice answer does not mean you should always go with C. When selecting items from a collection, independent events often contain selections made with replacement. So we take something out of a collection, maybe it's a hat, box, whatever, and we make note of it, and then we put it right back in. That's done with replacement. So example 2, a jar contains 10 blue, 12 black, and 15 red marbles. What is the probability of selecting a black marble, putting it back, and then selecting a blue marble? So we're reaching into this jar blindfolded, or maybe we can't see the contents at all, and we want to know what are the chances we draw a black marble out of the jar, put it back, and then select the blue marble. Well, the probability of drawing a black marble is we have a total of 37 marbles, so the probability of selecting a black marble is 12 out of 37. So that's our first event, is the probability of selecting a black marble. When we put it back, there are 37 marbles in the jar again. So because we put it back, that first selection back in, our denominator does not change because we still are going to have 37 marbles to choose from in our second event, which in this case is selecting a blue marble, which for that there's 10 of them. So to find this probability, we're going to multiply 12 37ths times 10 37ths and get 120 over 1,369. So a little bit less than 10% there. So whatever that percentage is, but as a fraction is 120 out of 1,369. All right, part B. What is the probability of selecting a red marble, putting it back, and then selecting another red marble? So drawing 2 red marbles with replacement. Another way to phrase this. So we still have 37 marbles in the jar. 15 of them are red. So we take 15 out of 37 for the first event, drawing a red marble. We put the marble back, so there's 37 marbles again. And then another red marble. Assuming that that first one was a red marble, we put it back, and we have 15 red marbles again. So it's 15 37ths times 15 37ths, or 15 37ths, that fraction squared, gives us 225 out of 1,369. Whatever that is a decimal in percent. All right, example 3, a certain blood test can determine the presence of a blood-borne pathogen 97% of the time. That is, if 100 people have the pathogen, then the test is going to confirm true for 97 of them. So 4 people with the pathogen are given the test. Find the probability that the test is accurate for all of them. So again, we have 4 people that we know have this pathogen, and they're given this test, which 97% of the people that have it, it's going to say that they have it. 3% of the time, it'll say they don't, so it'll give you a false negative in that case. So 4 people are tested. Find the probability that the test is accurate for all of them. Well, the probability that it's accurate for all is this probability that it's accurate for the first times the probability it's accurate for the second times the probability it's accurate for the third and times the probability it's accurate for the fourth. These are independent events when these people get tested because the first person's outcome, whether or not they have it, is not impacted at all for the second person's outcome, or I should say the second person's outcome is not impacted by the first person's outcome. So each one of these events are independent because none of the outcomes of any of them have an effect on the others. So this is just our multiplication rule extended out to 4 people instead of only 2. Well, we know that because each one of these are independent events, it's 97% for every single one of them. So 0.97 for the first times 0.97 for the second, 0.97 for the third, and 0.97 for the fourth. When we multiply that out, we get about 0.8853. So there's about an 88.53% chance that the test is going to be accurate for all 4 people. So, all right, that about does it for this video. Thank you for watching, and I will see you next time.